Okay, let's talk about the quantum mechanical model of the atom. And we're just going to do a very brief introduction of this, or to this, just to help you get a head start on where you're going to go with this before, or down the road. In grade 9 and 10, we use the Bohr-Rutherford model of the atom because it's a little bit simpler to understand, and it does work reasonably well for explaining and understanding a lot of the things we do in beginning chemistry, right, and learning about the basics of chemistry. But again, it is not a complete model, and so we have to sort of be aware of that when we use it, that it has limitations. It's a model that explains a lot of things, but it doesn't explain everything. And so we've developed in the last 70, 80 years another model that improves upon the Bohr-Rutherford model. We didn't abandon it altogether. We just fixed it up a bit. We tweaked it. And we tweaked it quite a bit. So now we understand a heck of a lot more. There may still be a few things that are difficult to explain, and this model may not be perfect, and maybe in a 50 or 60 years, somebody might improve it even more. But this is what we've got. So this model could be considered to be perhaps, our modern model, the one that we would actually use when we're getting high up into the world of chemistry and we want to explain very complicated things, right? It's got a funny name, quantum mechanics. The whole name of quantum mechanics, if I could simplify it, it comes down to one very important thing, and we've already talked about it. It's something that was suggested by a lot of people over the years, and it was the idea that things come in chunks. Remember, we talked about the idea that, when you look at a straight line, it might appear to be straight, but if you zoom in on it, it could be a chunky line, right? Up close, you see the chunks, but zoomed out from far away, you don't. You just see what looks like a straight line. And so we've been able to zero in on the universe with our new instruments and our devices that allow us to see lots of things our eyes cannot. We've been able to zoom in very, very close. And we've been able to do experiments and things that give us indirect evidence. Remember we talked about the wakes, seeing the wakes of a ship from high above, and how you could determine things about the boat even if you couldn't see the boat itself, just by looking at the wake it made in the water. So we do a lot of experiments and study how atoms disturb other things. And in those experiments, we have found that these experiments tend to suggest or support the idea that on the smallest level, things are chunky. So then you might ask the question, well, what's in between the chunks? And you might say, well, nothing. And then we start getting into philosophical arguments or discussions about what exactly is nothing. And it gets kind of crazy. Quantum mechanics is very difficult to understand, partially because there is very little in our real lives that we can use as an analogy or an example. We often use analogies where we'll say things like, well, it's like water that drips off a tree, or it's like this, or it's like that. But there's nothing in the world that quantum mechanics is like. So it becomes difficult because we're dealing with something we've never seen or experienced before. Anyway, the idea is that things come in little chunks, specific chunks, right? Each chunk has a very specific size, and we can actually measure that, and we understand how that works now with this complicated theory. And so what happens is if you take the model of the atom, the Bohr-Rutherford model, which was simply a nucleus with pluses in it for positives, right, and little n's for neutrons inside, and then we said the electrons happen to be the things that were on the outside. Originally, Rutherford imagined they were like zipping around like little planets in an orbit, something like that. And we were fixated on the position of the electrons. We were fixated on describing where they actually were. And we should then be able to go and say, okay, well, if the electron's going around in an orbit, I should be able to look right here when it goes by, and I should be able to find it, right? Just like if I'm watching Mars go around the sun, if I look in the right spot of its orbit, I should be able to find it. Well, the problem is that that's not what happened when we actually started looking. Things didn't work that way. And so what we discovered is that when you envision the world as coming in chunks, everything in chunks, energies in chunks, momentum, right? The way things are moving, all of that, comes in chunks. And so when you do that, it changes the way we look at this sort of little red orbit. And so what we did is we put the chunks into the equations. We can write equations for, this electron and this nucleus. We can write about how the positive charge tracks the negative charge. In grade 11 and 12, you will learn some of those equations. And you can actually get numbers, and you can calculate the amount of force that's holding it there. It's quite interesting if you're into that kind of thing. But for now, what we can say is that when you put the idea of chunks into those equations, you get very weird results. There was a fellow by the name of Schrodinger, and he wrote down what are called wave equations. And he was trying to use these equations to describe the actual path that the electrons took as they zipped around. And he found out that they don't actually have a definite path at all. It's almost like they're sort of all over the place, and finding them is extremely difficult at any given time. And if you do find one at a particular time, you have no way of really figuring out where it's going to be in 5 more minutes, which is kind of weird. Because if you watch a car go down the street and you see it here driving west and it's going so fast, you can predict in a few minutes that it's going to be down the road, and you can probably draw a circle around where it's likely going to end up. But we can't do that with electrons. So these wave equations allowed us to change our thinking. Now we don't look at where the electron is specifically. What we describe with our little sort of equation is where is the electron most likely to be found? That's what we're actually describing. Not where it is, but where's the best chance of finding it. So think about you right now, all right? So let's say, Mia's here today. It's her first day, so we'll use her as our example, all right? Let's say Mia forgot her lunch, and her mom wants to bring it to her. So her mom has to find out exactly where Mia is. So she can use latitude and longitude and find out exactly the point on Earth, right here where Mia is, right? But if she went to that spot, she'd also have to know that she's on the 2nd floor or the 3rd floor, right? Because if you just went to the latitude and longitude spot, you'd be at the bottom of the school, you'd be downstairs. It wouldn't work. But then she'd also have to know exactly what time to come. Because if she comes here in the afternoon, Mia won't be there. And of course, then it's too late for lunch anyway. And so if she gets all those numbers in place, she knows where she is, she knows what spot, she knows the time, and she comes here, she can be pretty sure that she's going to find Mia sitting in her desk, right? But maybe not. It's possible that at that moment, Mia got called to the office. Maybe Mia went to the bathroom, right? Maybe she's meeting some guy downstairs and they're doing some kind of illegal exchange. We don't know. We don't know what Mia's up to. And so we can only basically say that Mia's mother has a very good chance of finding Mia in her desk right now, because there are other factors, right, involved. And so the electron is kind of like that. If we go looking for it, we can determine where we most likely would find it, but it might not actually be there at that moment, which is a little bit strange. And so what we do is we put in the equations and we run the equation. So we take a nucleus like this, okay? And we use the equation for an electron in that very first orbit, right? That very first layer in the Bohr-Rutherford diagram. And we say, well, where is it? And what we find is if we do the equations and run them out, we get an answer here, this dot. And then we do them again, and we get an answer over here. And then we do them again, and we get an answer here. And we keep doing it, and what we find is this. We get answers that are sort of like this. But every once in a while, we get one over here. And maybe one down here. And then we get more up here. And then what's really weird is one answer is a dot that is so far away from this screen, it's down the street and, you know, in somebody's living room. It's like, oh, how did it get over there? I don't know, but that was only one answer. Most of the answers come out here. Okay, now you have to also remember I'm drawing this on a blackboard, or a whiteboard, sorry, that is flat. If you imagine this, it's kind of taking on a kind of circular shape, right? Imagine instead of a circle that it's ball shaped. It's also coming out around the outside where you can't really see on this picture. So it's kind of like an eggshell shape all around the nucleus, a tiny thin eggshell that surrounds the nucleus. That's where most of the dots go. Most of the times when we run the equation, that's where we find the answer. But we still do find weird answers that do not fit there. Here's a really weird thing. We might find an answer that puts the electron right inside the nucleus at that time for that run. That's weird. But then what we do is we look at it and we say, well, okay, you know, the time it was in the nucleus was only 1 out of, 650 billion tries. So we say that the chances of that happening are so slim, it's not even worth worrying about, really. And the chances of it being over here are like 1 in a million. But the chances of it being in this region right here are almost 100%, like 99.9999999874321%. And so we describe this as the most likely place to find that little electron. And it's a spherical shape, right? Spherical. So we call it the S orbital. And because it's the first one, we call it actually the 1s orbital. And that's where it would be. Now, if we take the second electron, let's say helium, which has 2 electrons, right? The other electron, where would it be? Well, it turns out that it can also be in this same little place. Because remember how 2 electrons work well together, right? The little magnetic parts match up quite nicely. And 2 electrons can fit together. And in harmony, they can be happy. But 3 is a crowd. And so the electrons in this 1s orbital, there can be 2 of them. 2 of them. Okay, so now what happens when we go to the next level? All right? If we go to the next level, what we find when we run the equations is we get some really cool results. We get, so here's the first level. I'm just going to dot it so we don't get confused. If we now do the equations for the electrons in the next level on the Bohr-Rutherford diagram, right? Remember how so here's our atom, and we have 2 electrons in the first level, and now we're working on this second level. If we do that, what we find is they all tend to clump around another spot, another eggshell that is further out. So it's like a nested eggshell. But here's the weird part. We call that the 2s orbital because it looks just like the 1 inside, but it's the second level, so we call it 2s. That makes sense, right? But we also see there are other places. The equations give us more results, not just those. And there's also a weird shape that occurs like this. This weird shape occurs. electrons could be in there. And we're like, whoa, that's what happens. All the dots, when we run the equations, they line up and give us this shape. And what's interesting is this shape could go this way, but it could also go this way. And I can't draw it, but you could imagine another one that came out of the board and into the board, right? Like with the X and Y axis and the Z axis, which would go in and out. I can't draw in and out, so like on the picture you can't see it, but you can imagine an in and out version as well. And that creates three. There's one. Okay. Here's the other. And then the one more sticking in and out of the board. So that produces what we call a p orbital. And there's one on the X, sort of lined up along X, right? We used to use X in math to mean the horizontal one. And then there's also a 2p y, which would be this up and down one here. And then there's one that's z. So what we discover with the equations is that the second level includes all of these. It includes a shell that looks like the first level, that holds 2 electrons. But it also has an extra 3 over here. And guess what? Each one of these can hold 2 electrons. You can put 2 in the px, 2 in the py, and 2 in the pz, because that's the rule, 2 per place. And when you add them up, 2, 4, 6, 8. Now we understand why you could get a maximum of 8 in the second level. And this carries on to the next level. In the third level, though, the equations give us an S, a 3S. Let's just pause for a second. Okay, we're back. So I'm going to move down. When we try to picture the third level, so now we're doing, the Bohr-Rutherford model if we fill that up and put 2 in the 2s and 2 in the 2px and 2 in the 2py and 2 in the 2pz, we get a total of 8, and it's full. There's no more. So then we go to the third level. Well, when we go to the third level, we get even more complicated when we do the equations. The numbers tell us that there's a nucleus. There's the 1s, I'm not going to draw it. And then there's the 2s, and all those blue ones we call the 2p's. I'm not going to draw them. But guess what? There's also out here, further out, a 3s. Another s orbital, which is another round spherical shell that's on the outside of the other two. And then there are 3 of the p orbitals outside that are bigger and further away than the 2p orbitals. And I've drawn 2 of them here, one on the y, one on the x, and there's also the one that goes in and out that I can't draw. So there's also 3 px and a py and a pz. But there is another pattern that emerges, which is very difficult to draw. So what I'll do is I'll jump over here to the internet and I'll search it out for you. Let's search it out. I'll just put atomic orbital shapes, and we should be able to grab a nice picture here. Okay. So this picture, here is what the S looks like. Right there at the top of the picture on the right-hand side, the red thing. Now, it's a shell. It's not a ball that's solid. You have to remember, it's like an eggshell. It's kind of hollow inside. And then here are the P's. Now, you can see they're like 2 little blobby guys, and they're trying to draw them right here in 3 different orientations. They're trying to draw 3D on a 2D sheet, which makes it hard. And here are the shapes of the next 5 at the third level. These are called the D orbitals. And there's 5 of them. Okay, I'll just come back to this later. That means there's also something called 3, and there's 3D. Now, we can't use X, Y, and Z because they're not really oriented that way. If you noticed, some of them are just weird shapes. Like this one is 4 little blobs, but look at this one. It's got a donut in the middle. So it becomes very difficult, right? And so what we call them becomes complicated. So we could just call them D1, D2, D3, D4, D5, or whatever, right? Just so we don't get confused. But there's 1, 2, 3, 4, 5 of them. And each of those can hold 2 electrons. So in the third level, we can put 2 electrons in the S. We can put 2 over here, and 2 over here, and 2 over here. There's the 8 again. And in grade 9, you said this orbital only holds 8, remember? But that's because you never went past calcium. Because when you get into the middle of the periodic table, that's where these D guys start showing up. And you can have 2 electrons in each one. So you can have 10 electrons there, 6 over here, and 2 over here. So the real story that they didn't tell you is that this can actually hold 18 electrons in that third level. But you never needed to know that because you never really went far enough down the list to hit those middle guys. Remember you called them the transition metals? We never looked at them because in order to understand how they work, we have to introduce this. And only the quantum mechanical model can help us understand how transition metals in the middle of the table work. So in grade 9, they just said, let's not go there. And we'll just pretend it's 8 up here. And it would be because you stop right here when you get to calcium. Okay? And that's how it changes. Now, there's another level. When we get further down, if we go to the next level, right, it gets more complicated still. The fourth level has a 4s shell, just like the first level. It also has p's, just like the second level. It also has d's, just like the third level. 5 of them. And guess what? If we run the equations, we get a whole other set of shapes called the 4f orbitals. And there are 7 possible shapes for F. 3, 4, 5, 6, 7. And their shapes are even stranger than the D shapes. As soon as you're done writing, I'll show you a picture of those shapes too. And you might, don't forget, how did we get these shapes? Well, we didn't just make them up. We used Schrodinger's equations that described positions of electrons using the chunky universe. And by doing that, we ended up getting all this stuff. Okay? Here at the bottom, down here, you can see all the D shapes. And they're very complicated, aren't they? And there are 7 possible arrangements. As far as we know, this is the end. But it doesn't have to be. We can run the equations for imaginary atoms that are even bigger. And we can get numbers. But we don't seem to see any of those atoms in real life. So as far as we can tell at this point, it stops after F because there are no atoms for real that are bigger than that. But we could imagine some. And some scientists have actually predicted what atoms might look like if they were bigger. And it's possible that there might be. You know, we have not seen everything the universe has to offer. So it's possible that at some point we're going to find more atoms that we never discovered before. We also discovered we can make atoms bigger by smashing them together. And we've been doing that for a couple of decades, and we've produced actual atoms that we've added to the periodic table. But what happens to atoms when they get big is they become unstable. You know, like when you're a little kid and you make a tower of Lego? You can only go so high, and then the tower falls over, right? No matter how hard you try, the tower will fall over. And so, no matter what, you can only get a certain height. It seems that you can only get atoms to a certain size, and then they fall apart. They just don't work. And of course, we have numbers in mathematics for that too. All right. So to summarize this model, what we find is that if we take the Bohr model, okay, so if I draw the Bohr-Rutherford model over here, and I put the orbitals, let me use a different color. I put the first, what we call the first orbital, or the first level, right? Well, in the first level, we have simply the 1s. And then if I take the second level of Niels Bohr's model and Rutherford's model, and I put it here, we find that it has an S-shaped orbital, but it also has the p, the x, the y, and the z orbitals. And if I take a third level, that third level has an s, it has p's, and it also has the 5 d's, d shapes. And then if I do one more, I'll do it in this purple color here. The purple orbital, the fourth level, has S, it has P shapes, it has D's, 5, 1, 2, 3, 4, 5, and now we have the 7, 3, 4, 5, 6, 7 F's. And so the real electron numbers are 2 in each one. And so the real electrons here, you would get 2 electrons. But here you'd get 2, 4, 6, 8 electrons. Here you'd get 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons. And on the bottom, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. You could get as many as 34 electrons, I think, if you use up all of those. And that's basically how we get the numbers to work out and how we can expand past calcium and look at what happens on the rest of the periodic table. But all we want to understand is this is the model that comes next, okay? I'm just telling you this so that next year it'll be like, oh yeah, I kind of remember how that works. And it's good to know that at least we're using a model that's slightly outdated and we're not using the most up-to-date model when we talk about Bohr and Rutherford. Now, this model is more complicated. There are rules as to how the electrons will fit into all these levels. And so you can see with all these levels and sub-levels and insides, it's quite complicated, right? But that's what the world is. It's complicated. And the more we learn about it, the more complicated it gets. So that's as far as we will go with the quantum mechanical model. Just remember that it's based on the idea that things are come in chunks. I know that sounds simple, but that tiny idea has turned into a massive, massive overhaul of physics and how we understand everything. And that this is what happens when you use the equations with the chunks. Okay? And you get these, and we can, and don't forget, this is not just an idea. We've done experiments that show that this is the case. Real life only works if we envision atoms to look like this. So that's why we use this model. Okay, we're going to stop there.